Hello grade 11s, today we're going to look at the sum of infinite number of terms. Oh, this is such a beautiful section, I hope you're going to enjoy it. So here's a bit of a joke, and I think you're not going to get the joke yet. So hopefully after completing this section or watching this video, you would see how hilarious this joke is. You won't stop laughing. An infinite number of mathematicians walk into a bar. The first one orders a beer. These are non-alcoholic ginger beers, of course. The second one orders half a beer. Third one orders a quarter of a beer. The fourth one would order an eighth of a beer, and the next one a 16th of a beer. You get the idea, so on. And the barman says, "You're all idiots!" And he pours 2 beers, and it will satisfy an infinite number of mathematicians. It's really funny. Let's understand why this is funny. So let's look at the sequence. So the sum of these terms. So the first one orders 1 ginger beer, the next one a half a ginger beer, then a quarter of a ginger beer, and an eighth, and a 16th, and so goes on. So let's find the sum of a couple of terms. So the first thing, let's work out the sum of the first. How many terms are there? 5 terms. What will the sum of the first 5 terms be? So you would say it is it's a geometric sequence, right? R to the n minus 1 over r minus 1. So the sum of the first 5 terms will be a is equal to 1, right? R is equal to, what happens to every single term? It halves, right? Everyone orders half the person before him ordered. So it's a half, and then how many terms are there? 5 minus 1 over a half minus 1. So the sum of the first 5 terms then, so the sum of the first 5 terms then is equal to 31 over 16. So for example, we wanted to find out the sum of the first 10 terms. So if this continues, like the next one would be 1 over 32, 1 over 64, and then 1 over 128, and so on. So we will do the same thing, right? It will be 1, the ratio is a half to the power of 10 now, minus 1, and that's over a half minus 1. So what's the sum of the first 10 terms going to be? So you just go back in your calculator, you change the 5 to a 10, and you're going to get 1023 over 512, which is equal to, if you just put that in decimals, it's equal to 1.998046, and so on. Okay, and just by the way, 31 over 16 was equal to 1.9375. So it appears like the more terms we add, the bigger the number gets. Of course, that would make sense, right? I mean, the more you're going to add, the higher it will get. Well, is it? So let's look at the sum of the first 20 terms. What's that going to be? So then it is 1. So it's a half to the power of 20 minus 1 over a half minus 1. So you just go back, and you change the 10 to the power of 10 to 20. That's the only thing there. And then you'll see that gets to 1.999999893. Ooh, okay. That's interesting. So let's work out the sum of the first 40 terms. What will the sum of the first 40 terms be? So then it is 1 half to the power of 40 minus 1 over a half minus 1. So the sum of the first 40 terms, change the 20 to a 40, and you're going to get 2. And if you find the sum of the first 100 terms, so in other words, if you make the 0.5 to the power of 40, if you make that, what did we say, 100, that is also equal to 2. And, even if you go up, if you make it 1,000, if you make 1,000,000 to the power of 1,000,000, in other words, n is equal to 1,000,000, add up 1,000,000 different terms, it's never going to exceed 2. So what on earth is happening here? So, good question, guys. Good question. So what happens is what happens is every single time you add another term, that term is the decimals of that term is so small it gets added on to the end. You follow it? If it's For example, if you've got 0.998, the next term's decimals is smaller than the 0.998. So it'll be like 0.0002, for example. Okay, so then if you add those up, you get 0.9982, So it just keeps on adding to the end. So that's why it's actually not getting any bigger. And we're going to do limits a bit in grade 12. And then, I mean, it's just fascinating. The AP kids know some of it. Although judging some of their marks, maybe not. But yeah, so that's the idea. So it doesn't matter. I mean, you can keep on adding more terms to it. It actually doesn't get any bigger. Kind of let you think of an asymptote, right? I mean, you're approaching, and you won't actually touch it. So it's that idea. So okay, so a couple of new terminology here, and so let's talk about that quickly. The first word we're going to look at is converging. Right, and then the opposite of converging is diverging. So you guys know what the word converging means, don't you? Converging means it tends towards, it's getting closer and closer. So it's how the sum, is just getting closer and closer to that definite limit. Okay, so that's converging. So it converges to a specific it converges to a specific point, all right? Diverging is just, it's getting either bigger, or it's getting smaller. So the sum of an arithmetic sequence, right, will just diverge. It will just get bigger. The more terms you add, the bigger it will get. Or the smaller it will get if the difference is negative, right? The smaller and smaller it will get. But some geometric sequences converges, okay? Okay, so some won't converge, right? If for example, if the ratio is equal to 2, okay? So let's have a sequence where the ratio is 2. So in other words, let's start with a number like 4, and the ratio is 2, so it's 8, and 16, and 32, and so onwards. The more of those terms I'm going to add, the bigger it's going to get. But say, for example, the ratio was a quarter. So if we had 4, the next one would be 1, right? And then it's a quarter, and then it's 1/16. That one, so this first part here would diverge, right? It will get bigger, the sum, the more terms you add. This one here would converge, right? So the more terms you're going to get, it's not actually going to make any difference up to a certain number of terms, of course. The sum won't exceed a certain number, and we're going to do limits again later. All right, so we need to understand when is something diverging, when is something converging. All right, so if none of the things made sense up to what I've just said now, then just look at this. So when you have a geometric sequence, right, and when the ratio is a proper fraction, in other words, if the ratio is between -1 and 1, okay, in other words, if the ratio is a half, a quarter, a fifth, a sixth, but it can't be -1 and it can't be 1. It can't be smaller than -1, can't be bigger than 1, right? Then it will converge, okay? Then that sequence, then the sum will converge, right? If the ratio of that geometric sequence is smaller than -1, greater than 1, that's the sum will diverge, right? It will get bigger, or smaller. It won't, okay. So what we've got the sum of an infinite number of terms, so that's the infinity sign, right? Oh goodness, that's not a good infinity sign. So that's the infinity sign, 8 that fell over. So it's equal to a over 1 minus the ratio. I'll put up the proof of that a bit later, how to derive that formula. Right, so the sum of infinite number of terms is equal to a divided by 1 minus the ratio. But just take note, the ratio, okay, so first of all, we need a geometric sequence, right? In other words, there must be a constant ratio. So the ratio we can find by term 2 divided by term 1, or term 3 divided by term 2. But what's very important here is the ratio must be between -1 and 1. Okay, so in the ratio, the numerator must be smaller than the denominator, if that makes sense. Okay, so let's hopefully that makes sense. So let's look at the same question now with those ginger ales. So we've got the first person ordering 1, and then a half, and then a quarter, and then an eighth, and then so onwards. Oh, that's a terrible color. So what we've got then, so A is equal to 1, and we've got the ratio is equal to a half. So therefore, the sum of an infinite number of terms is equal to A, which is equal to 1, divided by 1 minus the ratio, is a half. So therefore, the sum of infinite number of terms is 1 over a half, and 1 divided by a half is equal to 2. Right? So that's equal to 2. Isn't that beautiful? And that's what we saw earlier on. Remember that it doesn't matter how many terms you added. It's just getting, it was like 1.999, and then it like our term 40 was the same as term 100, right, or 1,000,000. So the sum is then equal to 2. Okay, so let's just recap what we've done so far. The sum, we can find the sum of an infinite number of terms, right? How cool is that? It doesn't matter how many of there are. The sum is not actually getting any bigger. But there's some limitations. Terms and conditions apply here. What's those terms and conditions? The ratio. Well, the first thing is it must be geometric sequence. The ratio must be between -1 and 1. All right. Okay, let's look at a couple of examples from your textbook. So calculate the sum of infinity of a geometric series. So yeah, I tell you it's a geometric series, and I tell you the sum of infinity. Not a lot of problems will be that explicit. So what we've got is we've got A, which is equal to a half, and then the ratio, which is equal to a half as well, right? If you multiply 1 over 2 to each term, you get the next term. So therefore, we can easily find the sum of infinite number of terms. So it's A over 1 minus the ratio. So the sum of infinite number of terms is equal to, it's a half divided by 1 minus a half. So that then is equal to a half divided by half, and that then is going to equal to 1. So that's not too bad, right? Example 34 there. So I ask you here to find the sum of a sequence that it starts, the bottom counter starts at 1, but the top it stops at infinity. But of course it doesn't stop at infinity, right? It's just continue forever. It's not like there's a gate and it said welcome to infinity and hey, how's it, you've reached it, it just continues forever. So in other words, it's a sigma sum. First question you're going to ask, of course, is, well, what do you need to do? You need to work out the first 3 terms. So in other words, term 1 plus term 2 plus term 3, and then dot 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 dot. Okay, so term 1 is going to be 2 times by 10, 1 minus, and then the bottom counter starts at 1. So that will be term 1. Term 2 would be 2 times by 10, and then it will be 1 minus, and then of course it increases by 1, right? So 1 minus 2. And then it goes 2, 10, and it's 1 minus, and it increases by 1, so it's 1 minus 3. And so it goes on. So therefore it will be 2 times by 10 to the power of 0 plus 2 times by 10 to the power of minus 1 plus 2 times by 10 to the power of minus 2, and we go on forever and ever. So that then is going to equal to 2 plus by, that's 2 over 10 plus 2 over 100 and forever. So therefore what do we have? We know that A is equal to 2, and we know that the ratio is equal to, yes, well done. Don't shout out. Put up your hand. It's equal to a 10th, right? And okay, so then they ask you, well, if it exists, what a strange thing to ask. How would you know if it exists? Well, it will only exist. You can only find the sum of an infinite number of terms if it's a geometric sequence, of course, and then the ratio is between -1 and 1. Is a 10th between -1 and 1? Is 0.1 between -1 and 1? Yes. So therefore, it will converge, right? New word of the day. So therefore, the sum of infinite number of terms, that's the one I want. So the sum of infinite number of terms is a over 1 minus the ratio. Sum of infinite number of terms is then equal to 2 over 1 minus a tenth. So you can type that in your calculator, but that it's actually quite beautiful. Look at that. So 1 minus the 10 minus 1 minus 1 over 10, 1 minus a tenth is equal to 2 divided by 9 over 10, which is equal to 20 divided by 9. Isn't that just too beautiful? Right, and if you're not sure, leave your answer in fraction form, simplified fraction form, but it's probably safe to just leave it as a decimal and round off to 2 decimal places. Right, let's look at example 36. These are very common questions. So consider the infinite geometric series. So it's p plus by p times by p plus by 1 plus by p times by p plus by 1 square. And then, of course, the next one will be times by p plus 1 cube. And it will continue forever. So for which values of p will this series converge? What the heck? So when will it converge? It will converge when the ratio is between minus 1 and 1, right? That's when it will converge. When it's a geometric series, but they told you it's a geometric series, that's cool. And when the ratio is between minus 1 and 1. In other words, first thing what we need to work out is what is the ratio? Good question, guys. What's the ratio? So the ratio is going to be what? What do I need to multiply to every single term to get to the next term? In other words, we can also work it out. What is term 2 divided by term 1? Or what is term 3 divided by term 2? But those must be the same, right? So term 2, so that's term 1, that's term 2, that's term 3. So term 2 is p times by p plus by 1 divided by p. And then term 3 is p plus by 1 squared divided by p plus by 1. So therefore that is equal to p plus by 1, and that there is also equal to p plus by 1, right? Cool. So the ratio, we said the ratio must be between minus 1 and 1, right? But what is the ratio now equal to? The ratio is p plus by 1. So p plus by 1 must be between minus 1 and 1. So therefore, what is p equal to? Remember how to do these inequalities. What you just do on one, you must do to the other one. So how do I get rid of the p plus 1? You only want p. So how do you get rid of the plus 1 there? You would minus, so you want to get rid of this plus 1 there, right? How do you get rid of it? You would minus 1, okay, but then you would minus 1 there, and of course you would minus 1 there. So, like a normal inequality, yeah? And so minus 1 is equal to minus 2, and then 1 minus 1 is equal to 0. That means p must be greater than minus 2, and p must be less than 0. So in other words, it starts at minus 2, and then goes up all the way to 0. For all the values for p between minus 2 and 0, that the sum will converge. Isn't that beautiful? All right. Question B. Assuming the series is convergent, calculate the sum of infinity. All right. For question B then, is assuming, okay, and so we need to calculate the sum to infinity. So that means A in this case is equal to P, and the ratio is equal to P plus by 1, and we need to find the sum of an infinite number of terms. So therefore, the sum of infinite number of terms is A over 1 minus the ratio. So that means A is equal to, in this case, well, A is equal to P, and it's 1 minus, and then the ratio is equal to P plus by 1. So that means it's P over, so 1 minus P plus by 1 is equal to, you must just, subtract the P and the 1 from that. So then you're just going to get P over minus P, which is equal to minus 1. Oh, that's a minus 1. So, right, so minus 1. All right, I think that's quite a nice question. Okay, so next one, example 37, a convergent geometric series, so you immediately know the ratios between minus 1 and 1, has a second term of 8 and a sum of infinity of 36. Determine the possible constant ratios. So in other words, in this case, we're going to get 2. That's why they say ratios. So let's go for it. So we've got, this is now very similar to those questions that Claire presented with a simultaneous equation part. You set up an equation, set up an equation, do two different, so solve them simultaneously. So what do we have here? We've got the second term of this sequence. What type of sequence is it? It's a geometric series, right? Term 2 is equal to 8. Okay, what does that mean? So it's a geometric series, so therefore the general term is, remember, ARn minus 1. So therefore 8 is equal to AR2 minus 1, right? N is equal to 2 and the answer is 8. So therefore AR to the 1, AR is equal to 8. Okay, so that's from the first piece of information. The second part is the sum of infinite number of terms is equal to 36. That means the sum of infinite number of terms, A1 minus the ratio, that is equal to 36, is equal to A1 minus the ratio. And then you just need to solve these two simultaneously. Alright. So what will we do? So I would get A or R alone in the first one. If we, for example, get A alone here in the first equation here, that means it's 8 over R, right? So what we can do then is we can then say, okay, so we've got that second equation. So when I'm talking about equation 1, of course, that's equation 1, and then that's equation 2. So what we're going to do is we're going to plug equation 1 right into equation 2. So let's look at it. So let's write down equation 2, 36 is equal to A over 1 minus the ratio, and we're going to substitute 8 of R into A. Alright, so therefore 36 is equal to 8 over R divided by, and then 1 minus the ratio. So multiply the 1 minus the ratio on both sides, so 36 times by 1 minus the ratio is equal to 8 divided by R. So 36 minus 36R is equal to 8 over R. Oh, you can already see what's happening, don't you? If you multiply R to every single term, what we're going to get is we're going to get, I kid you not, a quadratic. So therefore 36R squared minus 36R plus by 8, that must be equal to 0. Right, and then you can either simplify that or just use the quadratic formula, just bang that in your calculator. So then you're going to get two values for R. So R is equal to that, or R is equal to, so R is equal to 2/3, or R is equal to 1/3. How beautiful is that, eh? So, yeah, to determine the possible ratios, that's what we did.